Okay, so today we're going to talk about kinetics, and which we have discussed already, that kinetics has to do with how quickly we can get those molecules or substances to collide and form new substances. Um, so today we're going to talk about the beginnings of rate law. So it describes the dependence of the initial rate of a reaction on the concentration of its reactants. So the general equation for rate law is rate equals K times the concentration to the order. So K is a constant, and that constant of proportionality. It takes into account activation energy, the reaction of temperature at which the reaction occurs. And then N, and that should have been a little n, is the reaction order. And it determines how the rate depends on the concentration of the reactant. Okay, so if N is 0, then this is a zero order reaction. And that means the rate is independent of the concentration. So if I doubled my concentration, the rate still stays the same. So the rate does not change no matter what we do to the concentration. So a first order reaction, N equals 1, the rate is directly proportional to the concentration of A. So if my concentration goes up is times 2, then my reaction rate is 2 times bigger. If my concentration rate was 3 times bigger, then my reaction rate would be 3 times as fast. So into the second or a second order reaction, the reaction is proportional to the square of the concentration. So in this case, if N is 2, then our reaction rate quadruples between our time periods. So our reaction rate goes up times 4. This one is just going up the same amount as the concentration. This one, as our concentration doubles, our as our concentration doubles is times 2, then our reaction rate is times 4. This one, if our concentration doubles, our reaction rate doubles. And in the first one, if my concentration rate doubles, then my reaction rate is still unchanged. Okay, so the rate of the reaction is described in terms of the appearance of the product or the disappearance of the reactants. The rate law for a reaction can only be determined by experimental data. So we can't just look at an equation and guess what we think it is. It has to have experimental data. And these are just a couple of graphs. So in our first order, if you're looking at concentration versus time, in a first order, it goes down linearly. In a second order, because reaction rate is based on concentration, then it's going to go down exponentially, but at a fraction. And then if with the second order, even more so, because it's going up by 4 when it's doubled. And then if you look at the rate versus reaction concentration, for a zero order, the rate never changes. For a first order, it's linear. And for a second order, it is an exponential growth. And here are the formulas. And keep in mind, since anything to the 0 is 1, so in a 0 reaction rate, the rate is equal to K. It's equal to the constant. Okay, so the greater the value of the reactance exponent, and we are really only going to talk about the 3, 0, 1, and 2. There are others, and there are some that go to the half and to the 2.5. However, we won't see them on the AP test, and they are rare. Most reactions are going to fall into the 0, 1, or 2. Um, so the easiest way to find the exponents is to see what happens to the rate when the concentration of individual reactants is doubled. And we're looking at initial concentrations. Okay, so for 0 order, what we want to look at is no matter what our concentration is, our reaction rate stays the same. So these are all the same. We doubled our concentration, our initial rate stayed the same. We quadrupled it from here to here, and our reaction rate is still the same. So that is a 0 order. That's how you would recognize a 0 order. So a first order, they go up uh, directly. So if we double, then we double here. If we double from 20 to 40, then we double 30 to 60. If from going 10 to 40, that is 4 times. So 15 times 4 is 60. So these go up by the same amount. These go up proportionally the same. Okay, so when we look at second order, if we double our concentration, then our initial rate goes up times 4. So this was doubled, it went up by 2. This went up by 4. We doubled our concentration from 20 to 40 times 2. So this goes up times 4 from 60 to 240. Now, if we were looking at this and the numbers weren't so nice and neat, they weren't exactly doubled, and we needed to figure out what our order was, what our N was, then remember it is a proportionality. So we can take any two of these and figure out the ratio. So we'll take the rate divided by rate 1. And our rate is equal to K over the concentration to the nth power. And this is for the second concentration. And this is for the first concentration. And so we're going to look at these two here. So our K is going to cancel out because the K is the same for both because it's a constant. So it will be the same for both. So it's going to cancel out. So what we're left with is our rate for the second one was 240.240 moles per second. Moles per second. And our first one was 0.06 moles per second. Our K's canceled out. Our concentration for the first one, or for the second one, was 0.40 moles. And for the first one, it was 0.2 moles. This would be N2, N1. Okay, so we have what we wind up with now is this is 4. And this is going to be 40 divided by 0.4 divided by 0.2 is going to be 2 to the n. Because another way to write this would be 0.4, 0.2 n. So to determine our n, we take the log 4 is equal to n log 2. So n is equal to log 4 over log 2. You plug that into the calculator and you get n is 2. So it is a second order reaction. Okay, so if we have multiple reactants in a reaction, then we would add these orders together to get the order of the overall reaction. So the rate for the overall reaction is based on the order of the substance A and substance B combined. So for instance, if the order in reference to substance A was a 0 order and B was a second order, then the reaction would be a second order reaction. If A had been a first order, then the overall reaction would be a 3. Okay, so in this reaction, if we wanted to know what order for each of the components, then we were going to look at each one separately. So you want to find where, if we're looking at A, so 10 to 20, and you want to find where B and C stay the same between 20 and 10. So here 20 and 20 and 10 and 10. So we're going to look at this one for A. So as we doubled our concentration, our reaction rate quadrupled. So that means A is a fourth level. A is a second level order. So when we look at B, put 1.1, let's see. So from here to here, so here we'll look at this one and this one. Because between here and here, 10 and 10, 0.1 and 0.1, so those are the same. That's the only one that's different. So we doubled our concentration, and our reaction rate doubled. So that means B is a first level. And then C we will look here as we doubled our reaction rate, or as we doubled our concentration, our reaction rate stayed the same. So that means C is a zero order. I already talked about that. So the overall reaction the, of this particular experiment would have been 2 plus 1 is 3, so it would have had the reaction would have had an order of 3. But the reaction order in reference to A was was a second order in reference to B component. It was a first order, and in reference to C, it was a zero order. And that is all for today.